Hi, beautiful. Good morning. Oh, aren't you just adorable? Hey, beautiful. Hi, Patience. Say hi. Welcome to Lahar and Pestis. This is another episode of Science Monday, and I have spilled some water all over the top of my stove here. Oh, no, actually I haven't. This is just models for water. And I know what you're going to say, but Pestis, that's not water. The only water molecule that's there is one of those. Well, you're right, but you're also wrong, because those two are also water molecules. Most specifically, it's a hydronium ion and a hydroxide ion. And those are part of the natural makeup of water as well. And I'm going to show you that here in just a few minutes. That's what it's supposed to look like. Well, yes, that's what it's supposed to look like in an unnatural system. Water naturally dissociates to these. But past this, why are these red and why are those black? Well, it's because this company doesn't make oxygen molecules with 3 holes to represent the hydronium ion. Hey, Prentice Hall, if you ever watch this video, you need to fix that. Oxygens need to have 3 holes for making hydronium ions. See the difference? Alright, so, in case you can't tell, this is going to be a little bit about water and a little bit about a few other things. I need to try to help you understand that water chemistry consists of different things inside of it, okay? This is what everybody recognizes as being a water molecule, and yes, it is a water molecule. H2O is water. But water naturally disassociates with itself. So this will lose one of its hydrogens, and that hydrogen will be picked up by another water molecule, and that water molecule will turn into that and that. So 2 of these equals 2 of these, and these are always going to be in equal proportions in the water, in every source of water. So what is special about these 2 right here? Well, this one, known as the rolling molecule, this one is a hydroxide molecule, and it's got 1 oxygen, which is represented by the black sphere, and 1 hydrogen, which is represented by the white one that I'm holding on to. This is a base. This is what the basic molecule is for basicity in everything. This is a hydronium ion. It is 1 oxygen, represented by the black sphere, surrounded by 3 hydrogens, represented by the 3 white spheres. This is the hydronium ion, and this is what represents acidity or acid. This is the basic molecule of acidity. What makes them basic and what makes them acidic? Well, the acid, having 3 hydrogens here, this hydronium ion becomes positively charged. this oxygen becomes positively charged, and oxygen really, really hates being positively charged. I mean, it really dislikes it, and so it wants to get rid of one of those hydrogens, excuse me, really quickly, so it can go back to its natural state, the one that it wants to be in, a lot more easily. So what it does is it wants to, oh darn, these are hard to pull off. Hold on. So it wants to get rid of that and become that. That's where it is happiest at. This one really doesn't like being that way either, because it's more negative than it wants to be. So it is out hunting for one of these. And when it finds one, it's going to snap it up. It is going to snap it up, and it's going to become a water molecule again. Now, while these are out floating around, they are going to bump into each other. And the angle at which they bump into each other with can make them disassociate again. So these two water molecules can bump into each other, and this oxygen will steal that hydrogen, and you've disassociated water again. And this happens all of the time inside of water. Water dissociates, reassociates. All of these constituents make up water. And this is really important for the rest of the video.
Okay, so here in front of you, you will see a mortar that has got 3 aspirin inside of it, and I'm going to grind them up for the first step of the reaction. Again, this is aspirin being ground up to mix with the potassium permanganate. Alright, obviously I am pouring it into the reaction vessel here. And now I am going to mix and add the potassium permanganate to the vessel. I'm going to just add it straight into the same mortar, and I'm going to grind it with the leftover aspirin to try to get it all mixed up and to make the crystals of the potassium permanganate smaller, so that perhaps we can get a faster, more energetic reaction. Alright, adding it to the reaction vessel now, and I'm trying to clean it. And again, don't do this at home if you are not a chemist, and definitely don't do this at home if you're a kid. I'm combining the two powders together so that they have more surface area to contact each other with. Alright, this is water, and it is not tap water. It is filtered, the distilled water, and I am adding it to try to get the reaction to start. And this is kind of an experimental part here. I had no idea how much water I was going to need to add to the reaction to get it to start. All I knew is that I needed to have an amount of water in there, and as you can see, I turned it into a paste. I added entirely too much water, so the reaction is not going to start. I flooded it, basically smothered it completely. So you can hear a little bit of hissing now from the reaction. I've decided to go ahead and add more potassium permanganate so I can get closer to a stoichiometric amount. And I'm going to mix them together. Again, you can hear the hissing, but there is not very much of a vigorous reaction. And this is because later on I'll show you that there are not very many oxygens that can be oxidized, no alcohols that can be oxidized in aspirin. So here I'm going to add some glycerin to the reaction just to see if I can get any sort of thing going. And I eventually am able to get a reaction started with it. You can see it start to bubble and expand. That's the carbon dioxide being produced. And that brown color is the manganese dioxide and the diamanganese trioxide. It's providing that brown color. And again, that's a highly toxic substance. You don't want to mess with that. It's bad mojos. So I let the reaction die down, and I'm going to add a little bit more potassium permanganate, except this time I am doing it on the side of the reaction vessel to show you what kind of reaction we're comparing it to. This is our baseline reaction now. So I make a little divot and I begin to add a little bit of glycerin to it. And we can see with all the moisture nearby that the reaction between the glycerin and the potassium permanganate is almost instantaneous. We have almost instantaneous fire. That reaction can sometimes take as long as 30 seconds to start while it builds up enough of the hydroxide or the catalytic hydroxide or the catalytic water to start. Well, there we had enough water in the system that the reaction was able to happen almost instantaneously. I have washed the mortar and pestle and I have washed the bowl. I did take a safety container out there with me for disposing, and now I'm grinding up the Tylenol for the next demonstration. There is the ground Tylenol, and I am now going to add the potassium permanganate to it. This needs to be an approximate stoichiometric amount, so I need to put approximately the same amount of potassium permanganate as there is Tylenol. The Tylenol, if I remember correctly, was about 3.5 grams, so there is approximately 3.5 grams of potassium permanganate. Again, I'm going to mix the powders together so that they can have more surface area to react with each other. And now I'm going to add some water to it to try to get to the catalytic amount that is needed. This time I learned my lesson, and you'll notice that I only put a few drops. I did not flood the reaction. I did not saturate the reaction and turn it into a paste. And you can hear the reaction taking place. For comparison, I'm going to add a little bit of the tincture of potassium permanganate and water onto the side to try to help accelerate the reaction and to look for differences between the two. Here I'm playing with the bottle because I've noticed that I don't have enough potassium permanganate, so since I have this tincture that has a lot of potassium permanganate in it, I'm going to go on ahead and keep adding it to the system. And you can see that there is smoke and a little bit of flame that is starting with the Tylenol. And you'll notice later on, later on in the video, that the Tylenol does have alcohol and oxygens that can be oxidized. This is why that there is a reaction with the Tylenol. Here in a little bit, you'll see how vigorous it gets. You can hear the steam. So I have realized, again, like I said, that I needed to have more potassium permanganate, and here in a moment I will be adding more potassium permanganate to the system. This final addition of potassium permanganate and the final use of the tincture is going to produce the final reaction that you are about to see. And this is the proof that you need to have a catalytic amount of water or a catalytic amount of hydroxide, which can come from water, it can come from a tincture made of potassium permanganate and water, or it can come from the atmosphere. So thank you for spending your Monday with us, and see you soon. So what was all of that about that we just saw? What we saw was chemical reactions taking place. Specifically, we saw the proof of concept that you need to have a certain amount of water or the hydroxide ion known as a catalytic amount inside of your reaction to initiate the fire. This is the chemical equation for the potassium permanganate and glycerin reaction. This here is your potassium permanganate, and this here is your glycerin. This demonstrates the catalytic amount of water or hydroxide, and then this is the reaction arrow showing what's taking place. So we've got 14 potassium permanganate ions, 14 potassium permanganate molecules per each for every 4 glycerin molecules. And then that's going to give you a reaction that's going to produce 7 potassium carbonate, 5 5 carbon dioxide, 16 water, and 7 manganese trioxide. These are the products. This specific one right here that I'm circling now is what gives you the brown left over after the reaction. And this is a very, very good brown dye, but it's also pretty toxic. Down here, you'll see the actual number of atoms for each one of these added up together, so that you can see that the same number of atoms here ends up being the same number of atoms after the reaction, after the arrow. So we've got 14 potassiums, 14 manganese, 56 oxygen, 12 carbon, 12 more oxygen, and 32 hydrogens. And then there's your totals. You're going to have 14, 14, 68, 12, and 32. Over here, we're going to have the same thing. If you add up each individual molecule, we've got 14 potassium, 21 oxygen, and 7 carbon, plus 10 more oxygen and 5 more carbons, plus 32 hydrogens and 16 more oxygens, plus 14 manganese and 21 more oxygens. And that's going to result in the products that you see there. So the equation is what we call balanced. Okay, so now we're going to get into the reaction mechanisms themselves. So up here, where the cursor is circling, we've got the potassium permanganate, and here's the glycerin. When the two of them combine with each other, these arrows indicate what is going on when this happens, okay? So we've got this is known as an alcohol group or a hydroxyl group. And this oxygen from it is going to be attacking the manganese here. The manganese is then going to release its grip that it's got on this pair, on a pair of electrons, and these electrons are going to travel up and be solely contained here within the oxygen, and that's going to give you this intermediate right here. All right, this whole conglomerate here is the potassium permanganate and the glycerin. Okay, so next you're going to have the catalytic water or the atmospheric water or hydroxyl that we were talking about is going to come in, and it's going to abstract, or it's going to steal this hydrogen right here. And you'll notice that this oxygen is positive. You can barely see it in there right there. Okay, and you can see that this oxygen right here is positive. Alright, this positive oxygen wants to become negative. It doesn't like being positive like we talked about earlier. So it gives up this hydrogen very easily, and this is also a very good nucleophile. It likes to take those. So this is a very favorable reaction. And that is going to lead over here to this reaction, which is the energy producing reaction. Now, I've drawn out these bonds a little bit differently to show you how they're arranged, rather than it just being a group of carbon and hydrogen. This hydrogen here is coming out towards you. If you were to be looking at it at the molecular level, this hydrogen would kind of sort of be pointing at you. And this one would be pointing backwards through the screen towards, you know, the wall behind it, for example. So you're going to have another catalytic amount of oxygen, or hydroxyl group, or you're going to have catalytic water that's going to come in. It's going to abstract this hydrogen here, and that's going to leave this pair of electrons, because oxygen already has a pair of electrons that it wants to take that with. So this pair of electrons is going to join with this oxygen, and it's going to create a double bond right there. This pair of electrons from this oxygen is going to travel back to the manganese, and it's going to break this bond. And then this over here is going to grab another hydrogen from here, and this is going to create a hydroxyl group that is going to fall off because this oxygen negative, this electron pair, is going to take one of these hydrogens, and you're going to be left with this potassium manganate here. If you'll notice, it is different from the beginning one because now we have moved a hydrogen over to here, whereas there wasn't one previously. And we have also changed the location of the negative charge. Now this oxygen here is going to be different from the starting one here. You notice it doesn't have the hydrogen attached to it. It's no longer an alcohol group. And that is the first step of the energetic reaction. Now, this note over here, as you can see, it's going to happen to this one as well because the molecule is symmetrical. So I'm not going to redraw it out for the other side, just it could be either side because they're perfectly symmetrical. And here we have the second stage of the reaction, what is going to create the carboxylic acid here. And this is going to be the final energy stage of it. And this is also going to happen again on this side up here because the molecule is symmetrical. So we're going to have the catalytic amount of the hydroxide or water is going to come over here and it's going to attack this carbon, and this carbon is then going to release its grip on one of these electrons. It's going to come back up here to this oxygen, and what that's going to create is it's going to create this complex right here, which is glycerin with the carboxylic acid on the side because it comes from here. And again, I just drew this hydrogen right here on the bond that it would be at. Okay, so this complex that is formed by this reaction is then going to find another one of the potassium permanganate molecules in the complex, and the extra pair of electrons here is going to attack the manganese. Now this is a nucleophilic attack, and what it's going to do is this complex is going to be created from it. You'll notice that the manganese goes from having 4 oxygens to having 5 oxygens. This is an esterification. It's going to be 2 separate groups here that are going to be linked by an oxygen. Okay, now what's going to initiate the separation in the energy of this reaction is that this negative oxygen, this pair of electrons here, is going to attack this bond right here. Wait, that's not right. So this negative on the oxygen here, this extra pair of electrons, will go over and it will attack this hydrogen. The arrow I drew over a bit too far, and that's my fault, that's my bad. So it's going to abstract this hydrogen here. So what we're going to do to demonstrate that is I'm going to take one of the drawing utensils here, and you guys get to laugh at my elite sauce artistic skills. It's going to go there instead, and then this is the incorrect information. There, it is corrected. So this pair of electrons again will attack and abstract this hydrogen. That's going to let this pair of electrons join this bond right here, and that's going to create the carboxylic acid double bond to the oxygen here. This bond is going to break, and it's going to, these electrons are going to travel back over here to the manganese, and we're going to have the separation right here, and it's going to leave this glycerin here with a carboxylic acid, and once again, because it is a symmetrical molecule, this is going to happen on this side as well. And you're going to be left with, again, a protonated potassium permanganate molecule here. Now, as an addition, I want to point out that if you'll notice, the alcohols on the glycerin here are attached to only one thing. This makes them stick out. They're really, really easy to target. They're going to be the first ones that are going to be reacted in a reaction, and for that reason they are called primary alcohols. This one here is also only attached to one, but the carbon that it's attached to is attached to 2 things. If you see, this carbon here is attached to 1, this carbon here is only attached to 1, but this carbon is attached to 2. That makes this alcohol a secondary alcohol because it has what's known as steric hindrance. There is more bulk in the way, and it makes it harder to react with this oxygen, or I mean, excuse me, with this alcohol group. So this alcohol group is called a secondary alcohol group, and it is secondary because the molecule or the carbon that it's attached to is attached to two more molecules, or in this case atoms, excuse me. In this case they're carbons. And so there's a little bit of alcohol chemistry. Again, we've got primary alcohol here because the carbon is attached to only one other thing. Same thing over here because they're symmetrical. And this is a secondary alcohol because the carbon is attached to two other atoms. We're not counting hydrogens really in this group. In this, hydrogens usually are left out unless the reaction requires tracking the protons or the hydrogens. Like over here, we need to track the electrons, so I drew the electrons in, but here they're not here. It's for that reason. Okay, and here we are at the final reaction that I wanted to show you, the final energy producing reaction that I wanted to show you. And you'll notice that we're finally going to draw the steps for this alcohol group up here. And again, I want to reiterate that these are going to react first, this alcohol and this alcohol, because they are the primary alcohols. So this pair of electrons is going to attack this manganese group here. This set of electrons that's here, part of this bond, are going to travel up and join with this oxygen, making it like this one. This one's going to be a negatively charged oxygen. And you can see it here, and you can see it here. So we've got the two here, and we've got the complex formed. Once again, we've got our positively charged oxygen. Once again, we have got this oxygen out here that has the extra negative charge. And it's going to be the closest oxygen to this hydrogen. So if the hydrogen is flipped, it's going to be this one. And that's going to create this intermediate down here. And we're going to have a hydroxyl group. Again, it's going to be part of the catalytic atmospheric. However it gets there, it's going to be part of the catalytic amount. And it's going to abstract this proton that is right here. Okay? When it abstracts this proton, takes this proton, it's going to become water and it's going to be gone. It's no longer part of the equation. But this pair of electrons is once again going to jump down here, and it is going to attach itself to this oxygen, creating the carbon oxygen double bond here. And this pair is going to come back over here to the manganese, and of course we've got our protonated oxygen here, and it's going to result in our protonated manganate ion and our the beginning of our carboxylic acid on the glycerol. And then this would then enter into the reaction that we saw previously. We have the acetaminophen, and we have aspirin here, and then we've got naproxen, and we've got glucose. Now, if you look closely, you can see that we have got some similar patterns setting up that we have up here in the glycerol. Here on the acetaminophen, we have got a lone primary or a secondary alcohols, because this carbon here, which is what this is a carbon, is attached to two other carbons, and this is also a aromatic ring. So this is kind of bulky, but acetaminophen can be the alcohol group here. It can be oxidized to carboxylic acid by the potassium permanganate, which is why when in the video when you saw me grinding up the acetaminophen and pouring it in, we had reaction. You got to see all the boiling, the heat, the steam, and the camera didn't pick it up very well, but there was flame from it. So out in the like in the wild, in the woods, when you're lost or whatever, you could grind up your Tylenol and get a fire from it if you have potassium permanganate, and that would allow you to keep from having to carry the liquid glycerin with you, which if it ruptures inside of your bag, it can be all sorts of sticky and messy everywhere, and it can ruin a lot of things. Now, if you'll notice on the molecule next to it, aspirin, this is what I ground up and tried to use first. If you notice, there's already a double bond here for this oxygen, so this is only going to have one energy producing step. And if you go back and you listen, when I've added the potassium permanganate and some of the water to the aspirin, there was a little bit of hissing, but it was not a vigorous, violent reaction like compared to the acetaminophen or to the glycerin. This is an already formed carboxylic acid, so this cannot be oxidized any further, and the potassium permanganate is going to leave it alone. There's nothing else that it can do here. So aspirin is not a very good choice for um, having something to react with potassium permanganate. You're not going to get an energetic enough reaction, but you do get an energetic enough reaction from the acetaminophen here. This is not a carboxylic acid yet, so this can be reduced. So you've got 1, 2, 3 energy producing steps here that can be utilized by the potassium permanganate. Finally, over here, another common pain reliever that people carry with them is naproxen. This already has a carboxylic acid, so it cannot be oxidized by the um, potassium permanganate, and this oxygen here cannot be oxidized at all. It can't be targeted at all because, well, number one, there's a lot of steric hindrance here. There is no room for it to get in. The potassium permanganate molecule is a very large molecule. There's just no room for it here. So naproxen is not a good choice. I included glucose down here with its with the bonds and the directions of them, so that you can see that glucose has a whole lot of potential for this reaction. In fact, glucose. In a future video, I will visit glucose and potassium permanganate, attempting to make it a more vigorous reaction. But you can see here that glucose has a lot of free alcohol groups that can be oxidized completely. And finally, to conclude this video, we come back to the chemical equation to show you what all of these numbers mean and why I did this up this way to show it to you. If you'll notice that you need 14 potassium permanganates for every 4 glycerin molecules. And the way that you can maximize the reaction and the fire potential is by doing what we call a stoichiometric amount. That means that you put in the precise amount of the numbers of molecules into the reaction to try to get it to go to a complete conclusion. Where your energy comes from is by oxidizing the alcohols on the outside here. That's where the energy comes from. So you need to make sure that you completely oxidize as many of these as you can. And to do so, that means that you need to have a surplus amount of the potassium permanganate. So one of the things that I've seen, one of the errors that I've seen a lot of people do when they discuss this outdoors trick to start a fire, is they will put just a little bitty tiny pile of potassium permanganate and they'll cover it in glycerol. That's the wrong answer. You need to have at least 3.5 times as much potassium permanganate as you use for glycerin, and that is how you're going to maximize the heat generated by the reaction, and that's how you're going to start the reaction faster, and that is also how you're going to create a hotter reaction that will create a longer lasting fire. Thank you for joining us today for another episode of Science Monday. This is Pestis, and Lahar is under the weather today, so it's why you only get to listen to me. We hope you have a great day. We thank you for everything it is that you do for us.